ดักที่สี่แล้วปึ้มจะจบแล้วนี้สี่แล้วก็ทำการบ้านแล้วก็เสร็จแล้วน่าจะเสร็จได้ภายใน35 ชั่วโมงหนึ่งเนาะมันจะแบบเรียนได้สักครึ่งหนึ่งก่อนอะไรเดี๋ยวจบเร็วไป
We've shown how probabilistic graphical models can be used for a variety of inference tasks, like computing conditional probabilities or finding the map assignment. But often the thing that you actually want to do with a probability distribution is make decisions in the world. So for example, if you're a doctor encountering a patient, it's not just enough to figure out what disease the patient has. Ultimately, you need to decide what treatment to give the patient. How do we use a probability distribution, and specifically a probabilistic graphical model, in order to make good decisions? It turns out that the theoretical foundations for doing this kind of inference task were actually established long before probabilistic graphical models came to the forefront, and that framework is called the framework of maximum expected utility. So let's formulate the problem that we're trying to solve, and then we can define the principle of MEU, or maximum expected utility. So what does a simple decision-making situation D comprise of? Well, we have a set now. It's no longer a pure probabilistic model. We have other elements in it. We have an action A, which has several different choices that we might take. For example, different drugs that we might choose to give the patient. We have a set of states of the world, x1 up to xn, and the action can affect which of those states comes about. So this set of states might include both things that I can't affect, like the patient's predisposing factor of which disease they have or which test results came out which way, but it can also include things like the outcome that the patient will have after I administer the drug. So the set of variables that defines the state can involve things that I can affect and things that I cannot affect. And then finally, the final piece of the puzzle here is something that defines the agent's preferences. That is, I cannot make decisions that consider different actions without weighing the relative merits of different actions. And my way of evaluating the merits of different actions is to have some kind of numerical utility that tells me if I take action A and I have this particular state of the world, how happy am I? Very happy, moderately happy, or extremely unhappy. So this numerical utility function is going to be the thing that's going to allow me to evaluate different actions in terms of how much I prefer them. So now I can go ahead and write down the notion of an expected utility for a decision problem D given an action A. And the way in which that's done is a simple expectation. I sum up over all possible states of the world the probability that I get that state given the action, and remember, not everything in that state might be affected by the action, and then I multiply that by the utility of the state-action pair. And I sum up over all possible states that I might end up with, and that summation, that expectation, is the overall happiness that I have on average in this decision-making situation if I take the action A. Clearly, I want to maximize my overall happiness. And so the purpose of the maximum expected utility computation, the principle of maximum expected utility, maximum expected utility is that I want to choose the action A that maximizes this expected utility. We can use the ideas that we developed in the context of graphical models to represent decision-making situations in a very interpretable way. So this is a structure called an influence diagram, and it's an extension of a Bayesian network with two additional pieces. We have, in addition to random variables, which are denoted as usual as ovals, so here's a random variable, and a random variable is part of my state X. We also have two other kinds of nodes in this diagram. We have action variables, which are places where it's not nature that gets to make a choice over the value of the variable, but rather the agent that gets to pick. And then we have the green diamonds at the bottom, which represents utility. So let's look at this particular example, which is probably it's the simplest thing that you could construct. This is a budding entrepreneur who just graduated from college and wants to decide whether to found a widget-making company or not. So he has two possible actions, F0, which is do not found and go take a more conventional job. And this is found the company, which of course is a much more risky strategy. We have a random variable, which is the market for widgets. And this is a poor market, moderate, and a great market. And so now we can, and we have a probability distribution over those different values. The utility of the agent obviously depends on both whether he decides to found the company and on the market. And we're denoting that by having both of these be parents of the utility variable. So the parents of the utility variable or the utility function are the attributes or the variables on which the agent's utility depends. So in this case, our utility has two arguments, F and M. And we can see that if the agent decides not to found the company, then the utility is 0 regardless of the market conditions for widgets, because at that point you don't really care. And if the agent does decide to found the company and the market for widgets is poor, then his utility is -7. Say he invests a bunch of money and ends up losing all of it. If the market is moderate, his utility is 5. And if the market is great, his utility is 20. Okay? So now we can go ahead and compute expected utility for the two action choices. So in this case, the expected utility of F0 is 0. And the expected utility of F1 is going to be equal to 0.5 times -7 plus 0.3 times 5 plus 0.2 times 20, which, if you add it all up, is equal to 2. So obviously, in this case, the optimal action is to found the company. Let's look at a more complicated influence diagram that involves more random variables and also other richer structures. So this is an elaboration of our student network. It has the variables difficulty and intelligence, the grade, the quality of the letter, and in this case, also a variable that represents the job. Students' job prospects, which we're going to assume depend both on the quality of the letter as well as on the student's grade, because the recruiter has access to the student's transcript. The student has one decision in this example, which is whether to study in the course or not, which is going to probably affect their grade. And so we have that the study variable, the study action affects the distribution that the student has over grades. Now, in this case, you'll notice that we have three different utility diamonds: VG, VS, and VQ. So what are these? What do these represent? They represent different components of the utility function. So in this case, I've broken down the utility function into constituent pieces. This one represents the happiness with the grade by itself. This is the utility that you get from saying, yay, I got an A in the course. Or, ooh, not so good, I got a C. So that's one piece of your utility function. A second piece of your utility function is your overall career aspirations, which is the value of getting a good job versus not getting a good job. So that's this piece over here. And the final one is the component that is ascribed to the quality of life that you have during your studies. So if you don't study, maybe you can go and play ultimate frisbee and go to the movies every night. And so that might give you more happiness than sitting there hitting the books every evening. And so we're going to assume that that particular utility depends on how much you study and on how difficult the course is, because maybe it's more fun to study if it's easy. And we're going to assume that your overall utility, that the agent's overall utility is the sum of these different components. And this is called a decomposed utility function, and we'll come back to that later. Now you might wonder why I would bother decomposing the utility function instead of having just a single big monolithic utility function that is affected by all of these different factors. Well, that is exactly why, because it is in fact affected by all of these different factors. So whereas here I have a utility function that has one argument, and another one that has one argument, and one that has two arguments, if I had put them all together, I would have a single monolithic utility function that has four arguments, and that would be much harder to elicit because of the exponential combinatorial growth and the number of possible combinations that I need to consider. So this is a decomposition of a function, in this case the utility function, into factors in exactly the same way that we, for example, like to decompose a probability distribution as a product of factors. So another interesting extension that the influence diagram representation allows us to capture is the notion of the information available to the agent when they make their decision. So let's look at this example over here, which elaborates our entrepreneur example. And here we come in with the assumption that the entrepreneur has the opportunity to conduct a survey regarding the overall market demand for widgets before deciding whether to found the company. Now, the survey is not entirely reliable, and so over here we have the CPD that tells us how likely different survey results are to come up given different values of the true market demand. Now, the point is that having conducted the survey, the agent can base his decision on the value of the survey. And we denote that with the presence of an edge such as this, which indicates that the founder, that the entrepreneur can make different decisions depending on how the value of the survey turns out. So from a formal perspective, that means that what the agent's allowed to do is to choose a decision rule, which we're going to denote delta, at the action node. And what a decision rule is effectively a CPD. It tells the agent, given an assignment of the values to the parents of A, which are the variables that the agent can observe prior to making a decision, the agent, based on that, can decide on the probability distribution of the action that it takes in that particular situation. So here, for example, we would have a CPD, which tells us the probability of founding a company, which in this case is a binary value variable, given the three possible values of the survey variable. Now, you might say, why would I need to have a CPD? Why would the agent ever want to make a random choice between two different actions? And it turns out, in fact, that in a single agent decision-making situation, there is no value to allowing that extra expressive power because a deterministic CPD would work just as well. Nevertheless, for reasons that will become clear on the next slide, it's actually useful to think about this as a CPD, even though in most cases it'll actually be deterministic, at least in the examples that we're talking about. So now that we've given the agent that expressive power, how do you formulate the decision problem that they need to make? That is, what do they get to choose and how do they choose it? So given a decision rule delta for an action variable A, if we inject that into the decision network, now all of the variables in our network, both A and the remaining variables X all have a CPD associated with them. So now we have effectively defined a joint probability distribution over all the variables X union the variable A, because each of them has a CPD. And so this is this probability distribution. And the agent expected utility, once they've selected the decision rule delta A, is simply this expectation over here. We average out over all possible scenarios, where scenario is an assignment to the chance variables X as well as to the agent's action A. And what we're averaging out is the agent's utility in that scenario. And so that's the overall expectation that the agent, prior to anything going on, can expect to gain given a decision rule delta A. So obviously the agent wants to choose the decision rule delta A that is going to give him the maximum value for this expression that denotes his expected utility. And so this is the optimization problem that the agent is trying to solve. Okay. So how into the decision network, now all of the variables in our network, both A and the remaining variables X all have a CPD associated with them. So now we have effectively defined a joint probability distribution over all the variables X union the variable A, because each of them has a CPD. And so this is this probability distribution. And the agent expected utility, once they've selected the decision rule delta A, is simply this expectation over here. We average out over all possible scenarios, where scenario is an assignment to the chance variables X as well as to the agent's action A. And what we're averaging out is the agent's utility in that scenario. And so that's the overall expectation that the agent, prior to anything going on, can expect to gain given a decision rule delta A. So obviously the agent wants to choose the decision rule delta A that is going to give him the maximum value for this expression that denotes his expected utility. And so this is the optimization problem that the agent is trying to solve. So how do we go about finding the decision rule that maximizes the agent's expected utility? So let's look at this first in the context of a simple example, and then we'll do the general case. So over here, we see once more the expected utility equation for a given decision rule. And now we're trying to optimize this delta A. So let's write down the expected utility in this particular example. So the Bayesian network in this case has now two original CPDs. There's P of M that comes in from the M variable. There's P of S given M, which comes out from the survey variable. And we have the CPD that is as yet to be selected, which specifies the decision rule at the action F. And then multiplied with all that is the utility, which depends on the decision to found the company and on the true market value. Well, this should look awfully familiar. It is simply a product of factors. Some of these factors are probabilistic factors, and one of them, the U, is a different numerical factor, but it's still a factor, which depends on a scope of two variables, in this case, F and M. So now we can go ahead and apply the same kinds of analysis that we've done in previous computations. Specifically, we can, since we're trying to optimize over this expression over here, the delta F of F given S, we're going to push in everything that we don't currently need to manipulate, which is just F and S, which are the two things that appear in the factor of the decision rule. And so specifically, we're going to push in M and leave within the summation over M all of the factors that depend on M. And so that gives us a sum over M, P of S given M, U of F, comma M. And if we marginalize out M, what we end up with, if we multiply these three factors and marginalize out M, is a factor that we're going to call mu of Fs. And the reason that it's called mu is to suggest that it has a utility component U, so mu and U. now we have actually a fairly simple expression that the agent is trying to optimize. It's a summation over all possible values of S and F over here of the delta, the decision rule that the agent takes over F given the situation S, given the observation S, multiplied by this factor that I just computed. And now if our goal is now to optimize this expression, what the agent ought to do is to pick within this factor, mu of Fs, the highest value, the F that gives it the highest value in each circumstance S. So this is a little bit abstract, so let's look at this in the context of an actual numerical example to see this. So here are the three factors that we have in this network to begin with. This is the CPD for M over here, the CPD for S given M in the middle, and here is the utility factor U. It comes from here. And now if we're going to go through this expression, through this computation, and we're going to compute this expression over here, this is what we get. It's a factor that gives us this value for each value of the variable of the action F and each value of the survey variable S. And if we want to maximize this summation, and we look at this factor over here, it seems clear that what's going to maximize the summation is if we put full weight on F0 in the case S0, which if you think about, if you look at these CPDs, is the case where the survey suggests that the market demand is bad. And at the same time, in the other two cases, we're going to choose the action to found the company. And if you look at this, you can see that no other choice of delta is going to give us a higher value for this summation than this deterministic choice that chooses, in the case S0, we choose F0, and in the case S1 and S2, we choose to found company. And so this is the optimal decision rule. And if you ask what is the expectation, what is the agent's expected utility with this strategy before it does anything, before the survey is conducted, well, it's just going to be the sum of 0 plus 1.15 plus 2.1, which sums up to 2.25 as the overall expected utility, sorry, 3.25, as the agent's overall expected utility in this case. Now, if you think back to the agent's expected utility when it didn't have the information about the survey, that expected utility, if you recall, was 2. So without survey, the agent's best expected utility was equal to 2. So by conducting the survey, the agent has gained 1.25 utility points. So now let's generalize this to arbitrary decision diagrams. We're going to focus for the moment on single utility nodes and single action nodes. The more general case is a little bit more complicated, and we're not going to go through it, but the principles are very similar. So once again, going into this example, we see that delta A, the decision rule at A, defines a joint distribution over all of the chance nodes and the action node, and that is multiplied by the utility under this scenario. And so we can open up the probability distribution piece of delta A as a product of two types of CPDs. We have the original CPDs, which is simply the product over I, P of xi given its parents, and then we multiply that by the decision rule delta A. And we're going to use Z just as a shorthand to denote the parents, that is the observations. That the agent makes prior to deciding on A. So we can do the exact same moving in of factors inside and outside of the summation, and we're going to marginalize out everything except the factors, except the variables that appear in this factor delta A, so everything except A and its parent Z, and we're going to sum out all of the remaining variables, which for simplicity we're going to denote W. So this is summing up over all variables other than A and Z of this product of factors, including the utility variable, utility factor. And so we're going to get a utility factor just as we did before, which is a function of A and its parents. And we want to optimize the decision rule so as to maximize the possible summation over here. And once again, the optimal decision rule is just the one that picks for every combination of the parent Z, the action that gives us the maximum entry in this factor. So delta star of A Z is something that gives us a probability of 1. We start with probability 1, the action that gives us the argmax action for this factor, and any other action is selected with probability 0 in this conditioning case for Z. So summarizing how this algorithm goes, to compute the maximum expected utility and find the optimal decision rule at an action A, we take the following steps. We treat A as a random variable with, at this point, an unknown CPD. We introduce an additional factor beyond the CPDs, which is a utility factor whose scope is the variables that the utility depends on. So now we have, as usual, a collection of factors. We now do effectively a variable elimination algorithm. So this is plain, good old variable elimination to eliminate all variables except A and A's parents, which produces a factor mu sub AZ. And then for each parent assignment Z to the variable A, we choose the action that maximizes over A within that factor. So summarizing this, the MEU principle provides us with a rigorous foundation for decision-making under uncertainty. Building on that, the framework of probabilistic graphical models allows us to provide a compact representation for complicated high-dimensional decision-making settings where we have multiple chance variables, multiple actions, and utilities that depend on multiple variables. We can now build on inference methods in probabilistic graphical models, specifically in this case, the variable elimination algorithm, to both find the optimal strategy and figure out the overall value to the agent of a particular decision situation. And whereas we didn't talk about this, these methods can also be extended for richer scenarios where we have multiple utility components, as in the example that we gave, as well as multiple decisions that the agent makes in a sequence. When we talked about influence diagram, we included in the influence diagram nodes that represent the agent's utility function. And those utility functions, we said, indicate an agent's preferences regarding the state of the world or different aspects of the state of the world. What are these utility functions and where do they come from? So utility functions are necessary for our ability to compare complex scenarios that involve uncertainty or risk. It's not difficult for a person to say that they prefer an outcome where they get 4 million to one where they prefer 3 million. But it's not quite as easy to encode a more complicated preference that allows us to compare the utility of these two lotteries, as they're called, where the one on the left gives the agent $4 million with probability 0.2, and the one on the right gives the agent $3 million with probability 0.25. Which of those lotteries do we prefer if we had to make that decision? It turns out that the way to formalize the decisions-making process of an agent in this type of scenario is by ascribing a numerical utility to these different outcomes, to the outcome of 4 million, to the outcome 3 million, and to the outcome of $0. And then we can use the principle of maximum expected utility to decide between these two different lotteries. Specifically, we can then compare 0.2 times the utility of the outcome 4 million plus 0.8 to the utility of the outcome $0 versus the converse, which is 0.25, versus the expected utility for the second lottery, which is 0.25 times the utility of $3 million plus 0.75 times the utility of $0. And we can compare these two expressions and decide whether we prefer the one on the right, the one on the left, the one on the right, or they're equally good in our view. Now, it might be natural to assume that utility should be linear in the amount of payoff that we get, so that $5 is preferred about half as much as $10. It turns out that that's actually not the case for most people, and one example of that is this decision-making situation over here, where on the left the agent has the option of getting $4 million with probability 0.8, and on the right they have the option of getting $3 million with certainty. Most people tend to prefer the lottery on the right. But if one computes the expected payoff of these two different lotteries, we can see that the expected payoff over here is 4 million times 0.8, which is 3.2 million. Whereas on the right, we have an expected payoff of 3 million. So the expected payoff on this side is higher, and nevertheless, people prefer the lottery on the right. Another example, very famous example of this type of preference is what's called the St. Petersburg paradox. St. Petersburg paradox is an imaginary game that one can play where a fair coin is tossed repeatedly until it comes up heads for the first time. And if it comes up heads for the first time on the nth toss, you get 2 to the n dollars. Time on the nth toss, you get 2 to the n dollars. So what's the expected payoff in this case? Well, the probability that it comes up heads on the first toss is half, and then you get $2. The probability that it comes up heads for the first time is a quarter, and the payoff here is $4. third toss is eighth time 8 times $8, and it's easy to see that the expected payoff over here is infinite. So in principle, people might be willing to pay any amount to play this game because their expected payoff is bigger than any amount that they would be paying to play. But the fact is that for most people, the value of playing this game is approximately $2, which is a strong indication that their preferences are not linear in the amount of money that they earn. So let's try and quantify that using this notion, which is called a utility curve. The utility curve in this case has as the x-axis the dollar amount that you get, and on the y-axis the utility that an agent ascribes to that. And now let's compare a few different scenarios here. So first, let's look at the utility of getting $500. So if we go up from 500 to the utility curve, we can see that the utility of this outcome is going to fall over here. So this is going to be the utility of $500. But now let's look at a situation that involves some risk. So let's look at a set of lotteries where I get $0 with probability 1 minus p and $1,000 with probability p. Because of the linearity of expected utility, all of these lotteries are going to sit on this line over here, where depending on the value of p, I have a different weighted combination between getting the utility of $0 and the utility of $1,000. So for high values of p close to 1, we would be sitting on this side of the curve, and otherwise, for example, for low values of p, we would be sitting close to here. Specifically, what happens if we look at the probability p equals 0.5? Well, in that case, we would have this point on the curve over here. Now, the important thing to notice is that the utility of this point where I get $1,000 probability 50% and $0 probability 50%, that utility in this example is considerably lower than the utility of $500. So I prefer to get the $500 for certain, which is what most people would say. Now, if we look at what the lottery is worth, that is the risky version, we can see that that sits over here and might, for example, be corresponding to getting $400 with certainty. So that $400 is called the certainty equivalent of this lottery over here. That is, it's the amount that you'd be willing to trade for this lottery in terms of getting that money for certain. The difference between these two numbers, the expected reward and the utility of that lottery, is called the insurance premium or the risk premium. And it's called that because that's where insurance companies make their money, because of a person's willingness to take less money with certainty over a more risky proposition. So we can see that this kind of a curve that has this shape, this concave shape, is is representing a risk profile which is risk averse. That is, a person is willing to pay for taking less risk. Other profiles would of this curve would represent different behaviors. So, for example, if the utility was linear in the reward, that would be a behavior that was called risk neutral. Conversely, if we had a curve that looked like this, which is a convex function, that would be risk-seeking. And risk-seeking behavior occurs, for example, in Las Vegas, where one is willing, or in other gambling situations, where one is willing to actually take a loss in terms of the expected reward for the small chance of getting a really high payoff. Now, it turns out that people often have a utility curve that looks like the following. So if the x-axis is the amount of money that we get, and we arbitrarily place the 0 point over here, which is at one's current state, and we ask how much do you prefer to earn money and how much do you prefer to lose money, what's your utility for these different changes to one's state, we can see that one's preferences for earning money typically exhibit a form of diminishing returns, which gives us this concave utility curve, which suggests risk-averse behavior in the sense that we would prefer a certain amount of, we would prefer to get money with certainty relative to the expected, relative to the payoff equivalent uncertain lottery. Now, on the negative side of the spectrum, many people exhibit some kind of behavior that is actually more risk-seeking, which means that many people would prefer a small probability of a large loss relative to a small loss that you get with certainty. And that's a behavior that one often sees. More importantly, in this region of the space, which is close to one's current state, the behavior is often risk neutral. That is, small losses or small gains on the order of a small number of dollars, and of course it depends on one's baseline, are often something that you don't really care about having the uncertainty, and the expected payoff is often very close to the utility of the expected payoff. Now, one final important observation regarding utility functions is that one's utility often depends on many, many things, not just on the monetary gain. So, and all of the attributes that affect the preferences must be integrated into a single utility function. This is something that many people find very painful because it forces us to do things like put human life or the loss of human life on the same scale as monetary gain. The point is, even if we don't do this explicitly, even if we decline to put human life, for example, on the same scale as monetary gain, de facto our decisions are indicating that we're making those decisions. So, for example, when an airline chooses not to run maintenance on the airplane every single time that the airplane lands, that's a financial decision because that would be too costly, but at the same time, it also definitely increases the chance of loss of human life because of an accident. Now, it's not just big companies that make these decisions. We make these decisions ourselves. So we don't change the tires on our cars every month or every week because that would be too costly. But clearly having better tires is something that is likely to increase our chances of surviving an accident or a skid. So these trade-offs are ones that we make all the time, whether we recognize it or not. And so it's important when we think about a decision-making situation to list for ourselves all of the different things that could affect our decision: money, time, pleasure, and many, many other attributes, and think about how we could bring them together into a single utility function. Specifically in the context of human life, people have spent a lot of time thinking about how to bring in human life into one's utility function. And what turns out to be the wrong strategy in terms of reflecting people's preferences is to have a utility for the monolithic event of someone's death. And that turns out to be a very difficult thing to contemplate. What seems like a better strategy in general is this notion of a micromort, which is a 1 in a million chance of death. And so one puts the risk explicitly into the utility function. And so what is a 1 in a million chance of death worth? Well, back in 1980, so a while ago, people did this study, and it turns out that a micromort was worth approximately $20 in 1980 dollars. And so, of course, you can account for inflation, but it's not a huge amount of money. And that turns out to be a much better way of ranking people's utility for outcomes that involve risk to human life than asking about the utility of death. The second way that people use in medical decision-making situations, specifically for accounting for human life, is this notion of a QALY, or a quality-adjusted life year. So each quality-adjusted life year, which is a year adjusted for one's quality of life, has a certain utility associated with it, which allows it to be compared with other aspects that affect our utility in a decision-making situation. One example from a real-world situation is in this context of prenatal diagnosis, where researchers did extensive work in eliciting utility functions that involve prenatal testing. So relevant variables in this scenario include whether the baby is going to end up with some kind of genetic disorder, and specifically the one that they focused on was Down syndrome. But at the same time, there's other aspects that affect one's utility. So, for example, the pain of testing for Down syndrome is one aspect. The comfort of knowledge that you know what's going to happen is something that also turns out to contribute to one's utility function. Prenatal testing runs the risk of the loss of the fetus, and that is also clearly a component of one's utility function. And at the same time, the potential for future pregnancy, that is, whether there will be a future pregnancy or not, is another component of one's utility function. So if we think about the space here, the utility function depends in a complicated way on a large number on these 5 variables, and this is a fairly high dimensional space over which to elicit utilities. Fortunately, it turns out that many people have a lot of structure in their utility function, and specifically they can break down the utility function as a sum of subutilities, just as we had in the context of the influence diagrams. And for many people, that decomposition looks like the utility of the testing, a separate component for the utility of the peace of mind of knowledge. And then we have these two pairwise utility terms, the first of which is a term that depends simultaneously on Down syndrome and on the loss of the fetus. And the second is the utility that depends on the loss of the fetus and the potential for future pregnancy. So people's utility function, for many people, decomposes in this way, which it turns out we could actually think about as a graphical model that has singleton terms as well as these pairwise terms over here. And that allows us to considerably reduce the number of terms that we need to elicit in order to get a usable utility function. So to summarize, our utility function is what we can use to determine preferences about decisions that involve risk or uncertainty. In order to define or elicit a utility function, we generally need to consider multiple factors, all of which affect our utility. In most cases, the relationship between these different factors, between, say, money and the utility, or micromorts and the utility, this relationship is usually a nonlinear one, and the shape of the utility curve determines one's attitude towards risk. Finally, the actual utility function is usually a multi-attribute utility that integrates all of these different factors, and it often helps to decompose this utility function into tractable pieces, often as a sum of these pieces, which allows us to make this elicitation problem much more manageable. We showed how influence diagrams can allow an agent to make decisions regarding what course of action the agent should take given a set of observations. But often we want to answer a different type of question, which is, what observations should I even make before making the decision? For example, a doctor encountering a particular patient might have to decide which set of tests to perform on that patient. Tests are not free. They cause pain to the patient, they come with a risk, and they cost money. So which ones are worthwhile and which ones are not? The same kind of question comes up in many other scenarios. So for example, if you're running a sensor network, which sensor should I measure? The sensor might require energy in order to transmit the information, and that might be something that we want to consider carefully. And there's many other examples of that. It turns out that the same framework of influence diagrams can also be used to answer that question using rigorous formal foundations. So how do we provide a formal semantics for the notion of the value of getting information or the value of making an observation? So the formal definition that one can provide for this is the value of perfect information. So this stands for value of perfect information about a variable x is the value that we have by observing x before choosing an action at A. And perfect means that we observe x with perfectly, without any noise. So how do we make that a formal, how do we give that a formal value? Well, if D was our original influence diagram before I had the opportunity to observe x, we can compare the value of D to the value of a different influence diagram, which is the one where I introduce an edge from x to A. Because that tells me what the value of the situation would be if I had the ability to make that observation. So we can now define the value of perfect information to be simply a difference between the maximum expected utility that I have in the situation where I have this observation, minus the value, the expected utility to the agent in a scenario where I don't. So in this example that we've presented before, we saw that we compared two decision situations, one where the agent has found the company without any kind of additional information about the value of the market, and the other is where the agent gets to make an observation regarding the survey variable prior to making the decision whether to found the company. So we can compare the value of the decision-making situation with a variable from S to F minus the value of the decision-making situation, assuming the agent makes optimal decisions of the original decision-making situation B. And we can compare that and see how much the agent gained by this. And if you recall, we computed this to be 3.25, and this was 2. So the value of perfect information was 1.25, which means that the agent should be willing to pay anything up to 1.25 utility points in order to conduct the survey, because doing that will increase his expected utility. So let's look at some properties of the value of perfect information. So the first important property of the value of perfect information is assuming that there's no cost to the information, so not counting in how much it might cost, say, to conduct the survey. One can show that the value of perfect information is always greater than or equal to 0. So let's first go ahead and convince ourselves that this is true. So let's look at this expression over here, which compares the maximum expected utility between two different influence diagrams. And remember that each of these is obtained by optimizing over a decision rule. This one is optimizing, the MEU of the original decision D is optimizing a decision rule delta, which is a CPD of A given its current set of parents Z. And this one, the new influence diagram, is optimizing a decision rule delta where A has Z as all the original parent Z plus an additional parent X. And the point that becomes obvious when you think of it this way is that this is a strictly larger class of CPDs than this. That is, any CPD of the form delta of A given Z is also a CPD of the form delta of A given Z and X, which means any decision rule that I could have implemented in my original influence diagram, I can also implement in the context of my current influence diagram. And if it had a particular value there, it would still have that same expected utility value in the original diagram. So to go back to our example, for instance, if the agent has a decision rule that decides, say, to found the company regardless of the value of the survey, that is still a legitimate decision rule even when they get to observe the survey, and it would have exactly the same expected utility. And so that means that the set of decisions that I get to consider is just larger in the context of the richer influence diagram, and therefore one cannot possibly lose by exploring a larger space over which to optimize. Okay? So now let's think about the second property, which is when this value of perfect information is equal to 0. And this follows from a very similar reason to the one that we just talked about. So if the optimal decision rule for D, for my original influence diagram D, is still optimal for the extended influence diagram, then I've gained nothing from the information. That is, any decision rule that I could have applied before, I can still apply, and therefore I have gained nothing from this additional observation. And so this gives us a very clear notion of when information is useful. Information is useful precisely when it changes my decision. In at least one case. Which, thinking about this from the other perspective, if there is no ability for an observation to change my decision, there's really no point making it. Let's see how this intuition manifests in an actual decision-making scenario. So let's imagine that our entrepreneur has decided against founding a widget company and is now trying to pick between two companies that he can choose to join. For each company, there is the state that the company is in. So S1 is that the company doesn't have that great of a management, things are not necessarily going so well. So that's S1. S2 is medium, and S3 is the company is doing great. And that same thing holds for both companies. We are assuming that the company funders have access to some of this information about the company state because they can do some very in-depth due diligence. And so the chances of a company to get funding depends on the state of the company. So you can see that if the company state is poor, S1, then the chances of getting funding are 0.1, whereas if the company is doing great, the chances of getting funding are 0.9. And we're assuming that the agent's utility is 1 if the company that he joins gets funded, and 0 otherwise. So now let's think about the two strategies that the agent can take without any information. And so if the agent chooses to join company 1, one can see that company 1 is that the expected utility now is 0.72, and the expected utility of company 2, which is not doing as great, is only 0.33, which, if you look at the state of the company, that makes perfect sense. Now, what happens if the agent now gets to make an observation? And specifically, we're going to let the agent make the observation of S2, regarding S2, which is, in this case, the weaker of the two companies. So the agent has a little mole inside the company and can get access to that information before making his decision. What happens then? Well, if you look at the utility values, you can see that if company 2 is in state 1, then, which is a not unlikely scenario, it happens with probability 40%, the chances of getting funding are 0.1. And so the agent's expected utility in this case, so the expected utility if the agent chooses C2 and the state of the second company is S1, is 0.1. The expected utility if C equals C, if the agent chooses the second company and it's doing moderately well, is 0.4. Both of these are lower than the 0.72 that the agent can guarantee on expectation if he chooses company 1, even without any additional information on company 1. And so in both of these cases, the agent is going to prefer to stick with his original choice of going with company 1. It is only in the one scenario that we have where where the second company is doing really great, then his expected utility from going without company is 0.9, because that's the chances of getting funding in this case. And in that case, he would prefer to change his opinion and go with C2. But that happens with very low probability. It only happens with probability 0.1. And so that means that the value of information here is going to be very low, because although there is a situation in which the agent changes his mind, it's a very unlikely scenario. And sure enough, if you look at the expected utility in the influence diagram with that edge that I just added, it only goes up from 0.72 to 0.743, which means that the agent shouldn't be willing to pay his mole in company 2 too much money in order to get that information about company 2. Okay, now let's look at a slightly different situation where now neither company is doing so great. So you can see that now company 1 is also kind of this sort of rocky startup without a very good management structure and an unclear business model. In this case, what happens? So once again, we can compute the expected utility of the two actions. And now we can see that the expected utility of choosing company 1 is 0.35 as compared to the expected utility of company 2, which is 0.33. So now the decisions are much more finely balanced relative to each other. And so you would think that there would be a much higher value of information to be gained, because the chances that the agent would change his mind are considerably larger. So let's work our way through that and see that once again, if we consider adding this edge from the mole in company 2, we can now see that the agent is going to want to change his mind either when he observes S2 or when he observes S3, because both of these, both 0.4 and 0.9, are larger than the expected utility that he gets from sticking with company 1. And now, indeed, the expected utility goes up in the case where we have this influence diagram, and it goes up to 0.43, which is a much more significant increase in their expected utility relative to what we had before, because now there is more value to the information. We change, the agent changes their opinion in 2 out of 3 scenarios, and that's happens with probability 0.6. Now let's look at yet a third scenario where now we've changed the probability that the company gets funded. Now we're back in the bubble days of the internet boom, and basically pretty much every company gets funded with a pretty high probability, even if their business model is totally dubious. And in this case, what happens? So now we can once again compute the expected utility of C1, which is 0.788, the expected utility of C2, which is 0.779. And we can see that, again, these expected utilities are really close to each other. And intuitively, what that's going to mean is that even if the agent changes their mind, it doesn't make much of a difference in terms of their expected utility. So here we see that because of, in this case, we can see that 0.8, which is their expected utility in the case that they observe S2, this value S2, is bigger than 0.788, and so they're going to decide to change their mind and go from C1 to C2, and similarly for S3. But the actual utility gains in this case are fairly small. And so now the expected utility that we have in the scenario where the agent gets to observe this variable before making the decision is 0.8142, which is only a fairly small increase over the 0.788 that they could have guaranteed themselves without making that observation. So once again, this is a case where the poor mole in company 2 doesn't get that much money. So to summarize, influence diagrams provide a very clear and elegant interpretation for what it means to make an observation as simply the difference in the expected utility values, or the MEU values rather, between two influence diagrams. And this allows us to provide a concrete intuition about when information is valuable, and that is only and exactly when it induces a change in the action in at least one context, And now, quantitatively, it means that the extent to which information is valuable depends both on how much my utility improves based on that change and on how likely the contexts are in which I changed the decision.